to statistics, where you probably spend a lot of time learning how to compute these things in various mathematical or analytic ways. The primary difference of what I'm going to talk about today is how to compute them, doing it computationally rather than mathematically, and also a little bit about how to interpret what they mean. Probably the most important idea that I want to convey is that this is the right order of importance. If you measure something, the primary thing that I care about is the measurement that you made, the size of the effect. If that's all you tell me, that would probably be okay most of the time. Just tell me how big it is. My second question is going to be, how accurate is your measurement? Again, we're going to quantify the precision of the measurement, but I'm going to claim that this is a somewhat less important thing. And now a distant third important thing is to tell me whether the thing that you measured might actually be zero. Now, I'd like to have some notion of whether that might be true by chance or not. The problem that I see is that a lot of papers flip this around. So instead of effect size, most important thing, and p-value, distant third, what I often see is papers that have p-values in the abstract, as if it was the most important number, and no effect size in the whole paper. And I want to give you one example of this that drove me crazy a few years ago, but this is not the only example. I see this all the time. So you see things covered in newspapers, and they say, look, there's this effect size. This was an example of math anxiety in elementary school. If your teacher has more math anxiety, it turns out that the students perform less well on exams. So that's interesting. That's a surprising result. It might be important, but from reading this article in the newspaper, I had no idea how big the effect was. It said, in particular, it affected girls. It said for the boys, it didn't seem to matter whether the teacher was math anxious or not, but for the girls, it did, at least according to the study. The girls were more likely to do worse on the achievement exam if their teacher had more math anxiety. But no indication of how bad it actually is. So, all right, I went from the newspaper, I tracked down the actual article. This was in the Proceedings of the National Academy of Sciences, which is not a terrible venue. I assume it's been through peer review. I assume that one of those peer reviewers asked, how big is the effect? But I could not answer that question by reading the paper. I had to go onto the web page, get the supplementary material, go crawling through the tables, and I finally found out, okay, they had done regression analysis, they gave me the slope, they gave me the range of math anxiety for the teachers, and they gave me the summary statistics for the scores. So after I interpreted all the Greek letters and did a little bit of arithmetic on paper, what I finally figured out is that the difference between having the most anxious teacher or having the least anxious teacher worked out to be about half a point on a scale of 100. So I'm not very impressed by that, and I'm particularly annoyed that they made me do all that work to find out that the effect size here was statistically significant, but probably not actually important in practice. And that is a hugely important point, which is that statistical significance is just about p-values. It doesn't mean very much. What I really care about is whether the effect size matters. All right, that is the end of my rant. Let us get into the first notebook. So part one, as I mentioned, you should have the files that are in my repository. Part two, I'd like you to fire up Jupyter, load up the first notebook, which is effectsize.ipynb, read through that, execute the code, see what it does, and when you get to the first exercise, do some work on that. When you get to the part that says stop here, stop there. I want to make one other suggestion, which is consider working with a friend. So if you haven't done pair programming before, this is an excellent chance to try it out. Introduce yourself to a neighbor. A couple of reasons that this, I think, will help. One, you will have twice as much screen area. So one of you can have the slides or documentation up, and the other one can have the notebook and execute the code. The other is you've got two people to think at two different levels. So one of you can be thinking about understanding what's going on and thinking about what you should be doing, and the other one can be thinking about the details of Python and Jupyter and how to do what you should be doing. So take a minute. I dare you to introduce yourself to your neighbor, say hello, and consider working together. I won't require it, but I will require you to talk to each other, and I will come around and help. Okay, let me make a suggestion about how to work on all the exercises, which is you can decide how much you want to challenge yourself to do all these things without any help. If you want to do it without cheating and no looking, I will tip you off that almost everything can be done by copying and pasting from the examples above. So the intent of the exercises is really just to engage your brain into digesting some of the details and then putting them into use. If you find yourself stuck on something in an unproductive way, if you're working on it and just not making progress, one of the ways that you can cheat is for each notebook, like effect size, there's another notebook called effectsizesolution.ipynb. And if you open that up, you will discover that it has solutions to the exercise. So do whatever works best for you cognitively. Decide whether you want to engage with the exercises, or you could just run the solutions or copy from the solutions into the other notebook and play around with it. If people, raise your hand if you are close or nearly done, done or nearly done with the first exercise. Okay, so let me take a minute to just debrief on what we've seen so far. So one of the things here in passing is the random variables from scipy.stats. Have people seen random variables before from scipy.stats? Okay, so this is a newish thing to many of you. It's a pretty useful tool, so keep that in mind. We're not going to do a ton with it. I'm not going to get into details now, but you've seen it. Remember it. It'll come in handy later. Anytime you want to generate random values from a given distribution, this is very useful. In this case, we've created this object, which is a normal or a Gaussian distribution, and that object knows what its parameters are. It has the mean and the standard deviation of male and female heights, so we can use that to generate random values like these samples that we're working with. And the other thing that is there is evaluating the PDF, which is useful for making plots that look like that. So here we're just evaluating the PDF, the probability density function of the Gaussian distribution. So two things in passing that we get to see. And then the point of the exercise here is to take an absolute difference, which is measured in centimeters, and express that as a relative difference, which is expressed in percentage points. So that was part of the exercise here. And normally you just do that by taking the difference, so in this case a difference in means, and standardizing it by dividing through by the means themselves, or possibly the midpoint of the two means. And there are a couple of options here. Part of the reason I gave you this exercise is that you could have put the male mean in the denominator there, so that's one way to say it. The other possibility is to put the female mean there. And depending on the context, those will have slightly different senses. If you have two categories and one of them is sort of like a control group and one of them is a treatment group, then you might express the magnitude of the treatment relative to the mean of the control. That might be the natural thing to measure relative to. In this case, it's symmetric, so there's no obvious right way to put into the denominator there. So it's kind of an arbitrary choice, or you could just put the global mean for both groups. So that one's basically a warm-up. Hopefully that's making sense. If you have questions about it, this would be a good time for them. Anything? Okay. So that's just getting from an absolute difference to a relative difference. We'll go back into the notebook now. Again, feel free to work with a neighbor, work through the next section, and again, when you get to the part that says stop here, stop there. Okay, I want to walk through a couple of things that are in this part of the notebook. If you are working and making progress, you can feel free to ignore me, but I just want to point out a couple of things. So one of them, I want to put a threshold between these two means. There are a couple of ways to do that. One of them is to just pick the average of the two means, a mean of means. In this case, the two sample sizes are the same, so the mean of means is not terrible. An alternative, if they were different sizes, I could do a weighted mean of means. The other possibility is if you look at the two PDFs there, you might choose this point where the two PDFs cross over and choose that as the natural threshold between the two of them. And that's fine too. What I've given you in the notebook is a way of computing that thing. Turns out that that algebraic expression works out to be the point where those two PDFs are equal. I didn't do that analysis here, but if you have a question about it, I can show that to you. I've got two